Alright, in this mini lecture we're going to look at a way of classifying different types of dynamic systems and control systems. So I'll go ahead and start the presentation. There are fundamentally three different ways of looking at control systems and dynamic systems. And we're going to go ahead and start with the first way of looking at things that we're all very used to, which is the continuous time dynamic systems. So these are systems that are dynamic in nature, so they involve forces and moments, and they use continuous time variables, and that really is the world that we're used to, right? We're used to things that happen in a continuous way, and that really comes from the notion of Newtonian physics and Newtonian dynamics. We can break this world up into four different parts that do have intersections, as indicated by the diagram. And so the first thing that we would look at is what we would refer to as the linear or L systems. Now, the reason this is the first thing we look at is because it's actually one of the easier for us to analyze. It's not necessarily always an accurate representation of the physical world, but it is the type of system where we can do the most generalized analysis. And we're used to dealing with these kinds of systems. You've seen these in your math classes and in your physics classes. And it's how we model the world when we do sum of forces and whatnot. But linear systems have to obey two principles. They have to obey the principle or law of superposition, which means that if I operate on the sum of two variables, that's the same as operating on the variables independently and then adding them together. So I can superimpose solutions, right? We're used to doing that when we solve differential equations. We superimpose the homogeneous solution with the particular solution. And that is represented by this equation here, that f of x plus y equals f of x plus f of y. The second principle that linear systems have to obey is the idea of homogeneity. And that means that if I multiply a variable by a constant and then operate on it, so a times x, and then operate on it with f, that's the same as taking a times f operating on x. So this is essentially the same idea as a linear polynomial, right, where you have constant slope, or a linear equation. But this works for other operators like differential operators as well. And so from a differential equation point of view, this equation down here really represents kind of a generalized way of looking at linear differential equations. And the key to identifying linear differential equations is that there are no products of y or its derivatives. So I have no y times y or y times y dot. That's in this case down here for this differential equation. You would never see it. The minute you have a product of the variable you're trying to solve for here, so y, with itself or its derivatives, then that would be considered, that would not be a linear system. So what kind of system would you have? Well, you would have a nonlinear system. So a nonlinear system really is a broader class of systems which really contains all of the linear systems. But the nonlinear systems, here drawn separately, represent any kind of system that may have products of the thing we're taking the derivative of, say x here. So this equation right here is what's called a van der Pol oscillator, V-A-N-D-E-R-P-O-L, if you want to look it up, three different words, van der Pol oscillator. And notice it looks basically like an oscillator, except for this damping term here. Mu is a constant in this case. This damping term is proportional to x squared, and x is the variable that we would be solving for in this differential equation. So I've got x times itself giving me x squared times the derivative of x. So I've got a nonlinearity in this term right here. And this would violate the principle of superposition and homogeneity. Another type of common nonlinearity we can run into, which is something we saw the other day, is that I can have a function or an operator applied to the variable which I would be solving for. So this equation down here represents the solution, represents the motion for a pendulum. And to model it properly, we would use the sine of the angle, here u, but we linearized that, right, by assuming that the angle was small and that the sine of theta was approximately theta, or sine of u is approximately u. So we can linearize equations, which is something that you will learn about at some point down the road. So the nonlinear systems will be these N or NL systems. And then finally, we can look at, well, this idea of time varying. And it's not that the system itself is varying, doesn't evolve over time, right? All dynamic systems evolve over time. What we're really asking is, do the coefficients of the variable y themselves vary in time? And so that's what we would mean by a time varying system, is, say, for example, the stiffness coefficient could vary over time. All right, not just it's in a so the spring coefficient could vary in time, or the damping coefficient could vary in time, or the mass of the system could vary in time. And that's represented here by this generalized form of a nonlinear system where these Pn and Pn minus 1 and so on are coefficients of the variable y that we're going to solve for in the differential equation. And here are its higher derivatives. But notice they're functions of x, which is the time-like variable for this representation of the differential equation. So that would be a time-varying system. Finally, we could have a time-invariant system, which is where you have constant coefficients. So the coefficients don't vary in time. But notice y, in this case, the variable that we would be solving for in the differential equation, is a function of time, but the coefficients that multiply y and all its derivatives are not functions of time. And so we're going to constrain ourselves mostly to linear time invariant systems, or LTI. This is the type of system that is easiest for us to deal with initially. We can apply some very powerful solution techniques to that, to these kinds of systems, which we can't apply to others. And because we've really developed such a specific class of systems, these linear time invariant systems, we can solve, when we solve one, we'll know how to solve almost all of them. So again, the linear time invariant, or LTI systems, is where we'll concern, where we're going to spend most of our time on in the class. But of course, we could have nonlinear time invariant, or we could have nonlinear time varying, or we could have linear time varying systems. All of those would be valid representations of the system, some more difficult to analyze than others. So that's the continuous time world, and another way of looking at the world would be what we would refer to as the discrete time dynamic systems, or discrete time world. And there's transformation involved, and you can go back and forth between continuous and discrete time systems. We're not going to spend a lot of time in discrete time systems here because most of the dynamic systems we deal with are continuous in nature. But these are systems that are really, it's really a digital representation of the system. So using a computer to control a system, we get it to discrete time control. And in these cases, there's a fixed and finite time interval that we're using to analyze the system in. So in other words, variables evolved in fixed and finite time intervals. Whereas in continuous time, the variables evolve in infinitely small intervals of time. So we can also start to look at a way of classifying how our control system would interact with the physical world or the system dynamics. So in this case, we're going to distinguish between what is the system dynamics and what is the control system, and how do we go from one world to the other. So the system dynamics, as we've talked about, really represents the system itself that we're trying to control. So it's the physical world. We represent that abstractly as a system of mathematical equations, and we use Newton's laws. We use the free body diagrams. We use all of those tools to develop our mathematical models of the system. But it is just that. It's a representation of the system, the physical world that we're trying to understand. So to measure those systems that are in the physical world, we use sensors, and we've talked about this a bit. And those sensors could be anything from velocity, acceleration sensors, pressure sensors. They measure some physical variable of interest. And then to change the physical world, we use what we call actuators. And so those actuators, again, can be servos, ailerons, it could be heaters, it could be coolers, it could be all sorts of different devices. But again, it's how we go ahead and measure the physical world and how we interact or influence the physical world. And so the thing that we use to, if we're going to do this in a way that we're controlling, and I hate to use the word control to define this, but we build our own control system. So we measure something, we have an algorithm in our control system which tells us what to do with that information, which then gets fed to an actuator to cause some resulting influence on the physical world. As kind of a nice little example here, since this is aerospace, we could do something a little more concrete. I've got this spacecraft flying around the sun, and it's going to and measure, I don't know, it's doing something out there in space, right? So this spacecraft might want to change its position relative to the sun using a thruster, and so it would then go ahead and measure some sort of distance from the sun, and then it would use some sort of fancy computer here, like these are open source graphics that I could pull off, and then that computer would then tell say an ion thruster here what to do, fire or which direction to fire if we could change the direction of thrust. And then we would go ahead and measure again, and we would just keep doing that sort of thing over and over in this kind of loop. And that's the idea of this controlled system. We measure, we use that information in an algorithm, and then we actuate, and then we measure. And that's the classic feedback kind of loop. The next thing that we're going to look at here, and we're going to, again, as a way of partitioning out the worlds into different ways of looking at the world, and then identifying which ones we're going to look at here in class. There is this idea of classical control theory, or classical theory, and modern theory. And classical is classical in the sense that it goes back 100 and some odd years. Modern means, it goes back, say, 50 years, not too different. But really the main the main characteristic that distinguishes these two ways of looking at the world is in the modern theory, we're in the time domain. So everything is a function of time. And those are the kinds of equations of motion that we develop. They're functions of time. And so you might assume that it's natural to do the analysis in the time domain. But it turns out that it's not quite as easy to do for some kinds of systems. And so what we do is we take those time domain equations and we apply what's called the Laplace transform, and we'll look at how that works. And that Laplace transform converts the time domain system into the frequency domain system, or the complex domain, and we'll see where the term frequency comes from. But that gives us this classical theory. So it gives us a way of analyzing the world in the frequency domain, and that's referred to as classical control theory. We can always go back, of course, and we can use just the inverse Laplace transform, which we'll look at, which would then map us back into the modern or time domain world. So there you have it, an overview of 3 taxonomies, one which describes continuous time systems and discrete time systems and how they're related, and the fact that we're going to keep ourselves in this linear time invariant world for this class. We're going to mostly constrain ourselves to the classical theory of the frequency domain. We will discuss a little bit about how systems behave in time, but we're not going to spend a lot of time doing time domain control. We're going to do mostly frequency domain control. And then finally, I want to make it clear how actuators and sensors are used to interface with the physical world. But we're going to spend most of our time looking at how we develop the control systems, not necessarily on the physics or the engineering of sensors and actuators.